Section 2.1 functions is what's next on our radar. We mentioned this briefly in intermediate, not because I was teaching it, but I just sort of told you, hey, this is coming up. And so we talked about it briefly at the very end of intermediate when we were looking at whether graphs had certain kinds of symmetries. Remember when we looked at these graphs and we said, hey, it has x-axis symmetry or y-axis symmetry, origin symmetry, and I said this is related to the idea of functions, which we haven't gotten to yet. We'll see the relationship, not necessarily today, I don't think, but later. So we're going to take a look at what a function is first. A function is simply a rule that assigns each element in one set to a unique element in a second set. A little bit of vocabulary with that first. The input is the first set. The output is the second set. The independent variable is another phrasing for the input. Typically speaking for us, that's our x value when we're dealing with x's and y's. And it's also called the domain. And then the dependent variable is the output. Again, typically for us, that's the y, and this is the range. Domain and range are what's in parentheses. Domain, range. Yeah. Dependent just means it depends on something else, right? I mean, so the idea that y depends on what x is. That's why y is typically, the way it's worded and so forth, our dependent variable is because we determine y based on x values. So I'd like to give you several examples. I will start with something that is a word kind of problem, not word problem, but a like real life type of example with language. If I say with language, you guys won't freak out, right? Of course not. All right. Suppose C is the cost of mailing a letter. Funny enough, I'm sending my husband to mail something today. Yep, cost of mailing a letter, and W is the letter's weight. Is C a function of W? W a function of C? Both or neither? Okay, so C is cost. W is weight. And here's what the question's asking. If you know how much it costs, we'll deal with these one at a time. There's sort of three questions here, A and B, and then we'll be able to determine the both or the neither based on A and B, okay? Cost. If you know the cost to mail the letter, what's it cost to mail a letter right now? It's 50 something. We'll say 50 cents. I don't think that's right because I keep buying forever stamps, so I have no idea. I buy them in, not want to say in bulk, but like in sets of 20 or whatever. Let's say 50 cents. If you know that the letter costs 50 cents to mail, can you tell me without question how much weight it is? And I don't mean like, do you know it off the top of your head? But I mean, could you tell me if you were the clerk and you had the scale at the store that it's guaranteed going to be X number of ounces? No, you can't. So, Megan, do you know why? I saw you shaking your head first. Not sure? Kayla? I don't mean to be calling on you guys. I just thought maybe you had an idea of why. You're right.
Because you can't predict. That's why.
Not exactly. So have you ever been into the post office where you've given them a letter, they've weighed it, and they've said it's going to cost this amount of money to mail?
Yes.
Okay. So let's just think real practically speaking. If you mailed a letter to your grandma and you put one piece of paper inside the letter, and the next week you went and you mailed a letter to grandma and you put in 2 pieces of paper inside the letter, would they weigh something different?
Yeah.
Yes. Would you probably still have the same cost to mail the letter? Probably. There's a weight range that all cost the same amount of money. It's up to 1 ounce, actually. So anything less than 1 ounce. So you can typically get several sheets of paper, but they're not giving you a discount rate if you only put in 1 sheet of paper. Are you with me? Okay, now there comes a point when you have exceeded the 1 ounce and it's going to cost you the additional ounce postage. I mean, like that does happen. But there's a range of values that actually cost the same amount of money when you mail a letter. Does that make sense? So for a specific 50 cents, there's a range. It's 0 to 1 ounces. And of course, don't hold me to the 50 cents as being our current postage rate. I'll know, but it's something like that. I know it's higher than that actually, but. So you can't guarantee that when you know the postage price, that you know the weight of the letter. So the idea is that you could have this 50 cents and it could correspond to a 0.2 ounce package or letter, or a 0.5 ounce package or letter, or a 1 ounce package or letter, which means that the input being C, the cost, has multiple things in the range that it could correspond to. Does that make sense? So on the first one, is C a function of W? And the answer is no. Because one cost, and it doesn't even have to be 50 cents, right? It could be $1.22 or whatever. But one cost corresponds to one price. I'm sorry, I didn't say one price, I mean one price. One corresponds to multiple, I was already thinking about my next part, multiple weights. Okay, make sense? One cost corresponds to multiple weights. Tamaris.
How did you know that just from like this problem?
So some of your problems are going to have context within them that you should know, and some of them are going to assume you know a little bit about the context that's already presented there. So if you don't know a little bit about the context, you might have to actually search something like cost of mailing a letter. Like if you were doing this particular problem, you might, if you don't have any sort of prior experience or knowledge base of mailing a letter, you might have to actually Google online cost of mailing a letter, and it would give you some information that would help you out.
On a text, though? Like what if
It'll be something that you have context with that I feel comfortable with that doing, yeah. Or I won't have a problem that has context like this. It'll be a different kind of domain range question potentially.
Okay.
All right, let's go the other direction. So now let's say that you go into the post office and you give them their letter to mail, and it of course weighs one specific amount, right? You know what it's going to weigh when you don't necessarily know, but you know it's going to weigh one amount. Like I can't put it on the scale and it says, well, it might be 0.2 ounces and it might be 0.3 ounces, right? You know what it is. It's a specific weight. So when you put that letter on the scale and it's a specific weight, does it correspond to only one price when you mail it?
I mean, yes. Without range.
Yes. Yeah, not even within a range, but whatever your weight of your letter is, no matter what that is, it will have only one price when it outputs. Now, if you get a little creative, right, and you talk about, well, what if I overnight it and stuff like that, you're talking about far more variables. That's not what we're talking about here. We're just talking about your standard postage rate when you put that letter on the scale. There will be one weight. The person behind the counter will say, you need to pay me 57 cents or whatever it is, right? $1.27, I don't know. So if you go the other direction, so going this direction didn't work, right? When the cost was the input and the weight was the output, it didn't work. But if you go the other direction and you have the weight, one specific weight, so let's call it 0.5 ounces, it will have exactly one output, right? One cost to mail the letter. So on part B, this one is yes. Because one weight has only one cost. Right? So these weren't exactly A's and B's, but I think that, I put in my A and my B here. So both or neither, neither of those are correct now, right? Because they each individually, one of them worked and one of them didn't. Now, sometimes things work in both directions. Let me give you another word problem for which you do have context, but I want you to write it down so that you can think about it carefully, because if you think about it too fast, you're just going to make a mistake. Let's say, for instance, this isn't on my list, so I'm going to make it up at the end here. Let's say, for instance, that your input is a person, okay? So pick a person in your mind, whatever. And the output is biological mother. You got to be specific these days, you know. Okay. Would that work?
No.
If you take one person, do they have one and only one biological mother? Yes. Absolutely yes, says someone who gave birth. Right? Absolutely yes. And in fact, those people often refer to themselves as the real mother. Right? Y'all know what I'm talking about. Some of you have a personal experience. I do too, because I have kids in my house. Okay? But what if you go in the other direction? You're right. She could have multiple kids. Okay. So this works one direction. Okay. It works going from the person to the biological mother, but it doesn't work the other direction. It doesn't work going from the biological mother back to the person's, right? Because the biological mother could have multiple children.
So it doesn't work going to biological mother to the person because she could have multiple.
Right. So she could have child A and child B and child C.
Okay.
And so it doesn't work to go that direction. But it works to go the other way. Damaris?
Would that be the same if biological mother was under input and person wasn't, or does it have to be?
Right, I switched it. I was saying that if we went from input to output, this worked, but if I went the other way, I could rewrite it. If I put this one as the bio mom over here, and I tried to say went to person, right, or to their children, we'll say child. This one doesn't work because she could have multiple children. She could have child A, child B, child C. So that's why this one won't work. Okay? So again, that's why I was like, many of you did it. You said no very quickly, didn't you? Stop and think. Very careful about what the directions are saying, because the direction matters, right? The direction doesn't always matter, but a lot of times it will. Okay, let's do something that does not have context. Oh, well, actually, I've got one more slide before there with the vertical line test. Yeah, okay, let me do that. Vertical line test. A vertical line test says that a graph represents a function if and only if no vertical line is able to intersect the graph in more than one point. And I have 3 graphs to draw you, so while you're writing those details in or writing that down, if you don't already have it, I'm going to draw 3 graphs. This is, well, let me write. This is graph number 1. This is graph number 2. And this one's graph number 3. You may or may not recognize which each of those are the graphs of. That's sort of irrelevant at this point. But we're trying to see using the vertical line test if it represents a function. So visually, what we're doing is we're dropping vertical lines in. And what we want to ask ourselves as I drop these vertical lines is, does it ever cross more than once? And if the answer is yes, that it crosses more than once, then it's not a function. And if the answer is no, it never crosses more than once, then it is a function. Okay, so as I drop these vertical lines in my first problem, all the way across, infinitely many vertical lines there, right? Will it ever cross the graph more than once?
Yeah,
No, not the first one.
the graph, not the line.
Not the graph, the curved part, the part that I just drew in. It will never cross more than once. Because that's the case, this is a function. Yes. Now let's relate that back to the description over here. The description over here says that it's a function if every x value has only one y value. Those vertical lines that I dropped are equivalent to the x values. So maybe this is an x value of, say, -2. So at this x value of -2, there's exactly one y value. It's right there. Right? And red's terrible. I don't know why I've got red used here. Let's go with the, let me try blue. Is that any better?
Yeah.
Blue better? Okay. So there's exactly one y value for that x value. That's what vertical lines do. Vertical lines isolate a specific x value. And if they cross only once, then that means it corresponds to that specific location y value. So this represents a function. What happens if I draw vertical lines on part B, the circle?
They cross more than one.
Most of them, at least the ones I drew, they cross more than once. You might actually hit the edge and only cross once, or you might hit places where they don't cross. The problem spots are not the spots where they cross once or don't cross. The problem spots are the parts where they cross twice. And again, definitionally, the reason for that is because, say, this particular x value corresponds to a y value here and a y value here, right? It's the mom with 2 kids. That particular mom has 2 kids, one on top of the axis and one on bottom of the axis. So yeah, this is not a function. So the answer is no, it's not a function, and the reason is because it crosses in multiple places. It only has to do it once, but in multiple places it crosses the graph twice when I drop a vertical line. How about the third graph? Oh, let me ask a question, sorry, because the answers are yes and no. If I draw vertical lines, will it cross the graph twice? Yes. So is it a function? No. Good. Yes, ma'am, Madison.
Oh, sorry, I was just. No.
You're good?
No question, just
Okay.
resting on them here.
All right, no problem. So here's an example of a vertical line, right, that causes problems. Here would be another example of a vertical line that causes problems. It crosses twice. So it crosses twice, yes, which means it's not a function. Okay? So my yeses and nos are answering the question, does the graph represent a function? All right, so a function has this very unique situation where the input has to have only one output. But if you have other situations, or if you have a function situation, you actually have something called a relation. So a relation is a more general statement. A relation is simply a set of ordered pairs. There's no conditions. So 3 and 4 here are relations because they're sets of ordered pairs. Now, there's some directions on these, though, about these ordered pairs. These directions want us to decide if the relation actually represents a function. In other words, does every input have only one output? Now, we're going to look at it piecewise, and then I'm going to show you a diagram you could draw, too, if that makes you see it a little bit more clearly. So, for example, if I looked at the x value of 1, I know it corresponds to the value of 7. Are there any other ordered pairs that start out with 1? No. How about the number 0? The number 0 corresponds to 7. Does the number 0 show up at any other ordered pair? No. How about the number 4? No. Or the number 9? No. So this represents a function because every input that I underlined had only one output that it corresponded to. Okay?
Is the output the right number?
Yes. So the input,
So 1 and 0, don't they both have 7 though?
and this is output. But that's not the question, Damaris. The question is, does every input, 1, 0, 4, 9, have only one output?
Oh.
Yes. Now let me draw another picture because I don't necessarily think that the way that I just described it is always that intuitive. We could also talk about making a group of the inputs. The inputs were 1, 0, 4, and 9. And I'm going to make a group of my outputs over here. I have 7. I don't need to rewrite it twice. I know it shows up twice. And I have 6. Okay? So these are my inputs. These are my outputs. And I'm just going to draw an arrow showing which one it pairs up with. 1 corresponds to 7, and 0 corresponds to 7. 4 corresponds to 6, and 9 corresponds to 6. What I need for this to be a function is that the inputs have only one arrow leaving. I don't care how many outputs they correspond. I don't care how many outputs get an arrow coming to it. That part's okay. So I need only one, we'll call it an exit. Only one exiting arrow. Or exiting line. That's the condition. After that, it doesn't matter. The only one exiting line is the condition, and this meets it. So I have a function. Now, if I flip my ordered pairs, because that's exactly what happens on part B. These are the same list of numbers, but they're switched, right? So if I were to make my inputs now, I only have 7 and 6. And if I make my outputs, I have 1, 0, what else was it? 4 and 9. 1, 0, 4, 9. And if I draw these arrows, 7 goes to 1, and 7 goes to 0. 6 goes to 4, and 6 goes to 9. It's not a function because the inputs, at least one input, in fact both of them, but at least one input exited twice and went in 2 different directions, right? So this one is not a function.
Would you mind if we did it the first way you did it without drawing?
I don't care how you do it. I'm just trying to give you some options to think about it. Yep. Options to think about it. We'll say 7 goes to 0 and 1. 6 goes to 4 and 9. And again, it doesn't have to be that they both do it, but if at least one of them does it, it fails.
Do you have to explain it like that?
No, it didn't ask for an explanation, but I thought that it might be helpful if you were looking back at your notes later to decide what we were looking at, so you don't have to rewatch that portion of the video. Okay? All right, any questions on that? All right, specifically over here, I'm going to flip back real quick and make a note on something that I had you write down. Over here, when I wrote down the words domain and range do correspond to X and Y, and they do correspond to independent and dependent variables, but they're very specific. This notation, this description, is a description for functions. I don't expect that to cause a concern, but I just want you to realize there's a reason why, when I talk about the questions here, that some of these have a domain and range and other ones it doesn't make sense to talk about it that way, right? For example, for most of you, it doesn't make sense to talk about your children. You don't have any yet, right? But it makes sense for me to talk about children. So for some of these, it doesn't make sense to talk about domain and range because they don't even apply in the context of the problem. Now, the ones that we have questions about them, they will apply. So for example, 5 and number 6 and number 7 here correspond back to a couple of different problems. Number 5 says that it's going back to problem 2A. All right, so 2A was this graph. I got a mess on it. Well, we'll leave it. All right, ignore the fact that there's a -2 on there. It doesn't matter. This is my graph. This is 2A, right? It wants to know the domain and the range. All right, so domain and range is something that we haven't talked a whole lot about. Domain is X values, range is Y values. So here's how I think about the domain. Okay, I want to think about walking along, I'm sure this is close enough to hear me, walking along the X-axis, because the domain is supposed to be the X values. So if I'm walking along the X-axis, I'm always going to start from the left-hand side, from the left-hand side of the graph. That will be here for you guys, okay? And we're going to walk along the axis. And as I'm walking along the X-axis, I'm looking up and I'm looking down the whole time, okay? Up and down, up and down. Everybody good so far? I'm not going to do it real fast or I'll get dizzy. Okay, the question is, where do the values begin? Like when I'm walking from the farthest left to the farthest right, where do I first start seeing X values? Where first start seeing parts of my graph? And then where do I stop seeing parts of my graph? So on this one, we haven't done this yet, but on this one, it actually starts as far left as I want to go. This arrow here indicates it's going down and left forever, right? So no matter where I start on the left, I see values. I see them below at the beginning. And as I walk along, I see them, eventually I see them up above, and then I see them down below, and then I see them back up above, but I always see values. Does that make sense? So my domain on that first one,
All real numbers?
yeah, and there's actually a couple different ways that you can write that. So one way to write that is like this, all real numbers. I'm going to use, the hashtag that's not the hashtag. Pound sign. The other way that you could write that in an interval, because we talked about interval notation back in section 1.7, is -infinity to infinity. Starts at the far left, negative infinity, it goes to the far right, positive infinity. Okay? So if the domain x values means I'm walking along the x-axis, the range y values means I'm climbing up the y-axis like a ladder. Okay, let me go back to my picture. Went too far. There we go. So at this point now, I'm starting down here at the very bottom of the graph, and I'm climbing up a ladder. Okay? And instead of looking up and down, I'm looking left and right, because I'm moving vertically. I don't need to look up and down. I'm looking to the left and to the right. So for a while when I climb and I look to the left, I see values, right? I didn't mean to the left. Well, I guess it depends on your perspective. From where you're sitting, it's to the left, right? There's values right here. So as I'm climbing up the ladder, for a while I see the values over here to the left. There comes a point in the middle here where I see values both directions. That's fine. I still see values. It really doesn't matter if I see them more than once. I still see them. And as I keep climbing up, eventually I only see the values over here to the right. Correct? So this graph, as I'm continuing to climb up, I see values the entire time again. No matter how far low I start, no matter how far high I go, I will see values. So what do you suppose my range is for this one?
All real numbers.
Yeah, same thing. It's all real numbers. Or you can do the negative infinity to infinity. And again, when you're writing it down for me, it doesn't matter to me, but my math lab may ask for a specific type of written form, just so you know. It's the way it is.
Not my math lab.
Okay, what's that?
Not my math lab. It gives me a hard time.
I'm so sorry. All right, let's take a look back at number 3. This one wants number 3, domain and range, and it's actually this one. Again, the only one that we had a function for. So
Yay.
notice, I don't ask domain and range on B and C. They're not functions, doesn't make sense. And I don't ask domain and range on 4, because they're not function. It's not a function, so it doesn't make sense. So it's only referencing back to functions. All right, so number 3, domain and range. Domain's supposed to be the x values. Range is supposed to be the y values. And actually, this one's really nice because we already did that, right? We already wrote them down. And so we're going to write them down, but again, I'm going to show you how you can write them down in a way that would be most likely how you would be expected to write them on my math lab, I'm pretty sure. You have curly braces. Okay, a curly brace indicates it's all the values that occur inside. Typically, you probably would write them from smallest to largest. I don't know if my math lab will care, but just so that we're all clear, I think that they probably will want you to do them from decreasing to increasing. So they were 0, 1, 4, and 9 is my domain. And then for my range, it was just 6 and 7. Right? So sometimes when you're asked for domain and range, you're looking at a graph. Sometimes you're asked for domain and range, you're looking at a list of ordered pairs. Or perhaps, like number 7, you're looking at domain and range and you have an equation. So, is it possible to look at the graph of your equation to make decisions? It is. You have to be a little bit careful because sometimes your graph in your calculator, if you have a graphing calculator, doesn't show it the way that it really occurs. It does weird things, your calculator does. The calculator is only as small as the person who programmed it. You understand that, right? So there are glitches even within your calculator. There are sometimes things that you think you see that you don't. They're not really present there, and so forth. So looking at your graph is not necessarily a bad thing, but I think it's probably better as a check step than the only step. So let's actually talk about what would happen with domain and range. Domain, x values. Well, I have values underneath a radical, right? One of the things that you learned in the last chapter is that the values underneath the radical only have value in the real number system if they're positive underneath the radical or 0. Do you remember that? Yeah. So the values underneath a radical, in order to get a real number solution, have to be positive, which means that when I'm considering the domain, we're actually looking at the values where the underneath part of the radical is greater than or equal to 0. And there's that inequality that we learned how to solve in 1-7. We'll subtract the 5. I have negative x is greater than or equal to negative 5. I will multiply or divide by a negative 1. And that changes the direction of my sign. So now it says that my x value is less than or equal to, and it's positive 5.
How did you get the little symbol minus x.
Do you mean this symbol?
Yeah.
That's a greater than symbol. I know that I need to have values underneath the radical that are positive.
Okay.
So that's why I chose that symbol. It needs to be greater than 0 or equal to. So my domain starts at 5. I'm sorry, I didn't write that right. My domain is the values that are less than 5, so it starts at negative infinity and goes to 5.
Yeah.
Okay? Okay, range is actually easier. So we talked about the fact that when we put a square root onto a problem, we have to put a plus or a minus, right? Okay. But when the square root's already there, the assumption is that it's already just given to you the way it's supposed to be. Yes? We've talked about that in intermediate. I don't remember if we've said anything in the last chapter or not, but it's still a true statement. So there is an assumed, because you don't see it, positive value out here. Agreed? And you know that when you take a square root, positive things come out of it because of that, right? Okay. So the values that are coming out for y are going to be positive or what?
Negative.
No.
No.
0.
0.
You could get 0. Square root of 0 is 0. Okay? So anytime you're dealing with a radical, all the values that come out of the radical are either positive or 0. So my range is that my y values, I'll write it down here, my y values have to be coming out as greater than or equal to 0. Everything that comes out from underneath the radical is greater than or equal to 0. In fact, we knew that. That's why we wrote this down here, right? What were you saying, Maxwell?
Does that go for all radicals?
All radicals. If there'd been a negative in front, what do you think would happen?
You just flip the sign.
Yeah, everything coming out would be positive, but then multiplied by a negative, so it would be negative or 0 if there were a negative in front, but there isn't on this one.
Big brain.
All right, and then the interval notation for that is that it's 0 to infinity. All good? Okay. Again, could you graph it on your calculator and confirm that? Yeah, you could definitely do that. I have no problem with that. Just so you know what it will look like if you do, your graph will look like, make sure that I get it right. The graph will look like this. It will actually cross here at 5. Well, barely. It'll hit the axis at 5. That's what it will look like. All the y values are above the x-axis, right? Yep. And all the x values are from 5 to the left. So you should be able to visually confirm, based on what we talked about on problem number 5, that that matches the algebra that we just did with the inequalities. Okay, let's talk a little bit about notation. Function notation, specifically. Function notation looks like this. Okay? This is not g times x. Parentheses are sort of this unfortunate event that happened in mathematics where they have multiple meanings and it depends on where you are as to what they mean. I don't like it, but I didn't choose it. So when you see this notation, this means y. It means it's a function. And the way we read it, it's read as g of x, or f of x, or k of x, or h of x. That's how we read that notation. So if it bothers you to see it to start with, you're welcome to rewrite it. Just to remind yourself, this just means y equal x squared. Okay, it just means y equal x squared. But the reason that it's nice notation is because it tells you that the input is the letter x. So on the next part here where it says g of 2, this notation tells you replace x with 2. In other words, it wants you to do 2 squared. That's what it tells you. Without any words at all. It's just the notation. Replace x with 2. What is 2 squared? 4. The second piece says replace x with negative 2. What is negative 2 squared? 4. The answer is not going to always be 4, but it was on my 2 examples, right? But that's what that notation says. Replace that variable with this quantity instead. So this one down here, different equation, f of x squared minus x. This says replace the variable x with 2. It's there twice, so I replace it twice. Replace the x with 2. Just like that. Remember your order of operations. We will square the 2 first. We don't multiply by the 3 first. 2 squared is 4. 3 times 4 is minus 2 is 10. Okay? Now, this maybe looks a little bit weird, but it means the same thing. Replace the variable with w. Okay, so I just change all my x's to w's. That's all it says. Change all my x's to w's. All right, 3w squared minus w. I'm not going to get a number out of that one because it didn't give me a number input. It gave me a variable input. Okay, the last thing we have one more thing to do, but go ahead, Kaylee.
Would you just leave it like that?
Yep.
You can't.
There's no simplifying, no nothing.
Okay.
So in some sense, it looks weird, but it's actually far easier because I don't have to do anything, right? There's no simplification with arithmetic when I'm done.
No, not.
Okay, I'm going to teach you something that you may have seen done in a different way before. Has anybody heard of, I'm not going to ask you to tell me what it is, but has anybody heard of the phrase difference quotient? Yes. Okay. Sometimes you'll hear it done in an Algebra 2 class in high school. Maybe a pre-calculus class in high school. Depends on the curriculum and the way that they order things. The difference quotient looks like this. It's f of x plus h minus f of x over h. That's the difference quotient. If you've seen it before and or if you remember any of the details of it, I might be teaching it differently than you've seen before because I like this method. It breaks things down nicely. So here's what we do. This is the 3-step method, okay? Step number 1, and I'm going to label my steps because I want you to be able to look back and know what we did in each step. Step number 1 is to find f of x plus h. I will explain in a moment. Step number 2 is to subtract f of x. And step number 3 is to divide by h. This is the 3-step method. Now, if you look back at the difference quotient, it's all there. First, you find f of x plus h. Then you subtract f of x. And finally, you divide by h. It's just breaking down the 3 pieces. So we're going to do that for the function 3x squared minus x plus 7. Now, over here, the one we didn't like, the w at the end, or at least we thought maybe it looked weird, right? It just said replace x with w's. This notation says replace x with x plus h. So there's an x besides the 3, so now I'm going to have x plus h. There's an x by itself, so now I have an x plus h. And then I have my 7. Okay? Replaced my x's with x plus h's. Unlike this one over here, where there's nothing else I can do when I replaced my x's with w's, there is things I can do here. So in particular, we're going to multiply out x plus h times x plus h. You can, if you'd like, right now, go ahead and distribute this negative through. So negative x minus h plus 7. I'm going to move this step down because I'm going to need a little bit more space. If I distribute this out, I have x squared plus xh plus xh plus h squared. I will consolidate these two in the middle. That's 2xh, right? And then I will distribute my 3 through. So I would have 3x squared. Xh plus xh is 2xh times my 3 is 6xh. And then I have the 3h squared minus x minus h plus 7. The next two steps take what we just created, which is kind of a mess, and they make the mess clean up. So we take what we just created, 3x squared plus 6xh plus 3h squared minus x minus h plus 7, and I subtract off the original equation, 3x squared minus x plus 7. Now, if you want to, you can distribute the negative 3. You can. But the reality is this. Everything that's in this set of parentheses is going to cancel with something in front of it. Everything. So we're going to have 3 terms drop off immediately because I'm subtracting off 3 terms. Because this says 3x squared, and then this says I'm going to subtract 3x squared. This says negative h, and then this says I'm going to subtract a negative h. This says 7, and this says I'm going to subtract a 7. So I consolidate, I completely clean things up. The 3x squareds cancel. The x's cancel, and the 7's cancel. And I am left with 6xh plus 3h squared minus h. And here's the kicker. What you're left with better have an h in every term or you've made a mistake. There's an h in every single one of those pieces. Right? Yeah. And that's really important because the third step is to divide by h. 6xh plus 3h squared minus h divided by h. So the h will cancel with one of the h's in each of the pieces on top, which will leave me with 6x because the h divided out, 3h because I previously had h squared, and then h divided by h at the end is 1, so I have minus 1. Okay, I'm pretty sure, yes, I have one more difference quotient. What I'm going to do is I'm going to pause this at the moment. I'm going to let you guys clear out, and I'm going to record that one problem at the end so that when you pop back in later, all you have to watch is the last probably 2 to 3 minutes of the video, and you're done. You're set to go. All right, if you're tuning back in with us, we're doing our last example, number 11, which is the difference quotient, and I have a new function, g of x equals x squared minus x plus 3. So my first step is to calculate g of x plus h. So everywhere I have an x plus h, I will replace it with x plus h. So at the beginning I have x squared, so now I have x plus h squared. And then I had minus x, so now I'll have minus x plus h. And then I have plus 3. Just like before, we need to multiply x plus h times x plus h. And we can distribute this negative through. So I have negative x minus h and plus 3. All right, so at the beginning, we'll distribute this out. I have x squared plus xh plus xh plus h squared. And then again, minus the x minus the h and plus 3. The last step here would be to consolidate the two x plus h, xh's in the first part, so plus 2xh, and then plus h squared minus x minus h and plus 3. So we're done with step 1. We're on to step 2. Step 2 is to subtract g of x. Okay, so I'm just calling it g of x because it's the function. Previously I had f of x. So I write down everything from step number 1 just exactly like it appears. Okay, all the first step 1. And then I subtract and I write down g of x inside of the parentheses. X squared minus x plus 3. Again, you're welcome to distribute that negative through that parentheses if you wish, or you're just welcome to component-wise, oh, I forgot a squared here, sorry about that. To component-wise subtract things off, like this x squared, and then minus here with this x squared will cancel. This negative x, with this minus will cancel with this negative x. This positive 3 with this 3, this negative, will cancel with this 3. So what I'm left with is 2xh plus h squared minus h. And like I said in the earlier problem, you know that you've made a mistake if every term does not have an h in it. But of course, every term does. So that's a good sign. Our last step is to divide by h. So we're going to have 2xh plus h squared minus h divided by h. So this h cancels, one of the h squared h's cancels, and the h at the end cancels. So I have 2x at the beginning. In the middle, I had h squared, so now I have h. And at the end, the negative h divided by h is 1. Don't make it 0. It's an easy mistake to make. It is 1. And then we would be finished with the problem.